Okay, so all right, everyone, welcome back. This is a new section. This is 11.8. And 11.8, we want to study power series. Okay, so we're studying power series in 11.8. Now we'll start with the definition. Okay, so we'll try to define the power series itself. So now a power series, okay, so let me underline this guy, is of the form, you have a sum, n from 0 to infinity. This is Cn, which are the coefficients. X to the power of n equals, you have a C0 plus C1x plus C2x squared plus C3x cubed, on and on. Now, I need to mention that the power series is a special type of series. Okay, so let me define my terms. Where x is a variable, okay, so x is a variable, and the terms C sub n, right? These are the constants, and they are pretty much called the coefficient of the series. Okay, so the power series, of course, is a special type of series that has this form. You have the sum from, you're summing from 0 to infinity of Cn. Cn's are the constants, and we call them the coefficient of the series. And then you have x to the power of n. Now, you might have a question like, okay, so if these coefficients are the same, okay, suppose if Cn is just C, what happens? So that means the coefficients are equal. The coefficients Cn are equal. Now, when this happens, what difference does it make? Okay, so if I only need to change Cn to C. So that means that then I can write this sum going from 0 to infinity of Cn to the x to the power of n. Remember, your Cn is C, so just plug things in. Let's plug this guy to be C. You have x to the power of n. And this is going to be, you have a C, okay? Because C is fixed, right? It's just a constant. When n is 0, plug in 0 here. X to the power of 0 is 1, so you just have C. So then the next thing becomes Cx plus Cx squared plus Cx cubed, on and on, because these are infinite series, right? So, and then what is this guy itself? So this is a geometric series, which is a geometric series. With first term C, and what is the common ratio? The common ratio is actually what? X. Common ratio X. Okay, so there are a couple of things to take note of. I already mentioned earlier on that X is a variable, right? Okay, so let me just put that together here. Let me say notes. And there are three things I want you guys to take note of. Number one is that X is a variable. The second thing I want you to take note of is that we can actually think of a power series as a function of X. Okay, so I have as a function, of X. Now, what does that mean? It means I can be able to write my f of X So, okay, so I can define my power series in this manner, which this guy just C0. When you start running from, when you start moving from 0 to infinity, you have this guy. So x squared, of course, on and on. Okay. Now, take note, guys, warning, warning. This, your f of x here, is not a polynomial. Okay. So you might be forced to think that's a polynomial, but not quite, because when we talk about polynomials, polynomials have finite sum, but these guys are infinite. Okay. So this is like Cn, Xn, then you go on and on. So not a polynomial, since a polynomial is a finite sum. Right? Makes sense? Now, the third thing I want you to take note of as we start building from, from the scratch. So for each value of x, now this third thing is very important, guys. For each value of x, we can actually test, for convergence or divergence. Okay, so it's going to make sense at some point when we, when we move on, but just take note of these three important things right now, because they will help our understanding going forward, right? Now, a couple of, another definition. So, because I want to state a couple of definitions before we, before we really apply them. So definition, the domain of a function. Remember, we can write the power series as a function, right? We just saw that some second ago. The domain of this function, Cn, Xn, is the set. Is the set of all x for which the series converge. Now, if I have a power series and I have a question like, okay, what is the domain of the function? Remember, we already established that we can write a power series as a function, right? So I can ask you for the domain of that function. That domain, of course, think about calculus 1. When you find the domain of function, you're talking about values of x for which the function is satisfied, right? Or for which the function exists. So, but right now, when we talk about power series, we're talking about the set of these values of x for which this series converges, okay? Now, let me give, let's see this very simple example. The power series from 0 to infinity Cn Xn. This power series, now where, let me fix the constant, okay? Suppose the constant is fixed. Where C is a constant. Now this power series, okay, converges when this guy is less than 1. Do you remember geometric series? Because we said above that this guy is a geometric series, okay? So when does it converge? When the common ratio is less than 1, okay? So, and diverges when this guy, or diverges for this guy greater than or equal to 1. Now, so what do we know? So my f of x, remember I can write my power series as a function, okay? So this is c x to the n. Now, what is the domain? We said the domain is the set of values of s for which it converges. So, and here we already have a statement like this guy converge for this guy, okay? So this guy has a domain. This is the domain. Now, if you really want to write it in interval form, of course, you know, we can always do that. In interval form, I can just say, or this is -1 to less than x less than 1. If I don't like it this way, I can just write -1, 1. So the domain is either this guy, or you just say -1, 1. So that's the set of the values of x for which that series converges. Okay, so it's all coming together to fit into a whole piece, you know, then we see how to apply them in different ways and in different manners. So let's have another definition. So I always advise that you have like a note card. You know, I know these definitions differs. I know the tests that we've done in the past, we actually have different tests. Now, power series is not like a test for series. It's like a special series itself. Remember when we looked at geometric series, right? So this is a special series, okay? So a series, now we want to define another series. Okay, a series of the form. This is another way to think about power series, okay? A series of the form, you have n from 0 to infinity, Cn x minus a to the power of n. All right, so now I don't want to lose anyone, guys. Let me write this down. So now we are going to get into some technical details in a bit. So you want to make sure I don't lose you at any point. So this is Cn x minus a to the power of n. Now, when n is going from 0, this guy is C0 plus C1 x minus a plus C2 x minus, let's write this better, s minus a squared, right? Plus this can go on and on. A series of this form is called a power series. But not just a power series in x minus a. Okay, so a power series in x minus a. If you don't want to call it that, you can just say, or we call it a power series centered at a. If you don't want to think about it that way, we have 3 different ways to refer to it, or a power series about a. So what is the summary of what we're saying? If I give you a power series in x minus a, something like this, Cn x minus a to the power of n. This a here is what we call the center. Okay, take note because we need that idea. That a is what we call the center. Now we've had some different definitions. Now let's start applying and see how you apply or see how you treat this kind of power series. Example. So we want to ask, for what value of x does the following power series converge? For what values of x does the following power series converge? We're going to have 2 of them. The first one we look at is this guy, and from 0 to infinity, n factorial x to the power of n. And then we'll move on to this other one. When n goes from 1 to infinity, you have a -1 to the power of n minus 1, x to the power of n divided by n. Okay, so things are getting interesting. Okay, in the past, we have not studied series that looks like this. Okay, so because if you think about the kind of series we've seen in the past, we could have seen something that is like this. Let's think about this too, right? We could have seen something like this. Okay, but there has not been anything that has like x this way. So hence, this is different from what we've done before. And we really need to, you know, I want you to follow me closely so that I don't lose you, okay? So for what values of x does this power series, or do these power series converge? Solution. Let's start with the first one. The first one is a bit easier to handle. N goes from 0 to infinity. You got a n factorial x to the power of n. Now, we really need to determine what values of x it converges. A key thing, or one important test when you do the power series, is the ratio test. Okay, ratio test is a very important series test. Yes, when you do power series, keep that in mind, guys. Ratio test. Okay, can I remind you guys about the ratio test? Limits as n goes large, an plus 1 over an equals L. This L can be three different things. It can be less than 1. This L can be equal to 1. And this L can be greater than 1. When it is less than 1, what happens? It converges. When it is equal to 1, what happens? Inconclusive. When it is bigger than 1, what happens? Diverges. Okay? So yeah, I need my ratio test. So what is A sub n? Now, how do you know power series? I think we already answered that, okay, by the definition we gave. Power series always look like this guy. You will have, especially be on the lookout for this variable, this part, okay? So, but in this case, my an is just this n factorial. What about my n factorial xn? Sorry. Let me write this down. This is my an, okay? What about a sub n plus 1? Because I need it, right? A sub n plus 1. Wherever you have n, plug in n plus 1. So you have n plus 1 factorial. This is xn plus 1. Okay, it's looking interesting already. Now let's see if we can simplify an plus 1. This is n plus 1 factorial. Remember, we saw that in the last session we did. This guy can be interpreted as this. And this is x to the power of n times x to the power of 1. Of course, we've seen that again. So let me remind you, n plus 1 factorial is n plus 1 multiplied by n factorial. Okay, so let's get down to the limits. N goes large. This is n plus 1, right? You got an n factorial, x to the power of n times x. Okay, so all divided by, what is a sub n? N factorial x to the power of n. Okay, interesting. So some things can actually cancel. This guy can take off this guy. And this guy can actually knock off this guy. So really, what are we left with? Limit as n goes large, n plus 1. You have x right here, okay? Nothing on the bottom. So I have n, I have x and then n plus 1. But n plus 1, of course, is positive because your n is going from 0, okay? So that means I can write this guy as limit as n goes large, n plus 1, and then absolute value of x. Now be careful, you cannot take the absolute value sign away from x because you don't know if x is positive or not. So you have to maintain that with your x and maintain the absolute value with x. Okay, so now let's find these limits. As n goes large, what happens? This guy is just undefined. Okay, so what do we say now? By the ratio test, what happens? The series does what? Diverges. Now we have to think about something, guys. Okay. See what we really have to think about. Okay, so let me go this way. I'm gonna write this again, but I don't want you guys to get confused. So let me say A. Now look at this. You have absolute value of X. X can be a negative number, X can be a positive number, X can be 0. So when X is not equal to 0, what is this limit? The limit as n goes large of n plus 1, this guy, is undefined. Now, remember, the power series is a special series and it needs some kind of special treatment. So I have to pay attention to my X. Is the X going to be a negative number? Is it going to be a positive number? Is it going to be 0? So, but remember, even if X is a negative number, the absolute value takes care of the negative sign. If X is a positive number, then the absolute value sign don't matter, right? But we have to pay attention, close attention to whether X is 0 or not 0, okay? Not 0 already accounts for whether positive or negative. So conclusion here is that the series diverges by the ratio test. Now, the second component you really have to be on the lookout for. So now what happens when X is 0? Talk to me, guys. When X is 0, okay, so when X is 0, what happens? The limit as n goes large, n plus 1. Remember, this guy is 0, so this is like a multiply by 0 thing. And the whole of this guy is just going to be what? 0. But what that means, your L is 0. 0 is a number less than 1. So what happens? So the series converges when X equals 0 by the ratio test. This is when X is not 0. Now you can begin to see that there are different behaviors. Series behave in some type of way. In 11.6, we looked at absolute convergence, right? That a series may not converge absolutely. That doesn't mean that the original series without the absolute value diverges. No. So there are some certain type of behaviors that we really need to factor in when we treat power series. Okay. So we got to this point and we had absolute value of X. I mean, we're not sure what type of value is X. It could have been a number that is not equal to 0. If we say it's a number not equal to 0, it can be positive or negative. And it can also be 0 itself. Now, when it's different from 0, you check the behavior, okay? You check the convergence or divergence of the series. And when it is equal to 0 also, you have that same liberty to check whether it does converge or diverge. Okay, so I hope it's all making sense so far. Okay, good. So now let's look at another example, the second example we left on top. And that was this guy we really wanted to deal with, this guy. Power of n divided by n. Okay, so where do I start from? Where do I start from? Now remember that we said that we can always write power series as a function. So that means that I can say let f of x equals this guy. Okay, so what is my an? Negative 1 to the power of n minus 1, x to the power of n over n. You have your an, which is the whole of this guy. Remember that always. This is my a sub n. What is my a sub n plus 1? That means wherever I have n, go ahead and plug in n plus 1. So this guy is negative 1. Then you do have a n plus 1 minus 1. This is x. This is n plus 1, all divided by n plus 1. So now always try to see if you can factor or simplify your a sub n plus 1. Okay. So this is n plus 1 minus 1. This guy cancels. So I do have a negative 1 to the power n here. I can split this guy by indices. Now, keep in mind that whenever you do the ratio test, something has to cancel, okay? Some parts have to cancel for the most part. So now let's get down to our ratio test. Okay, so this is negative 1 to the power of n. Remember, it's an plus 1 over an, right? Then you're passing the limit. All divided by, you got an n plus 1. Okay, so but that's your a. The whole of this guy now I have here now is my a sub n plus 1. What about my a sub n? This guy is a rational function kind of thing, right? It has a top and a bottom. So that means that once you put it here, change flip, this guy becomes n divided by negative 1 to the power of n times negative 1 to the power of negative 1. You have x to the power of n. So what am I doing? So this is just me also trying to split things up here. Okay. So let's see, can anything cancel? This guy takes off this guy. This guy gets rid of this guy. So we have limit as n goes large. Now, you are dealing with the absolute value, right? Keep that in mind. This negative has no say because absolute value of a negative number gives you positive. So that means on the top, you have a n divided by n plus 1 multiplied by x. Because you have to remember what remains, right? N divided by n plus 1 is always positive. So I can drop the absolute value around that guy, okay? All right, so we're back at it. We're back here, guys. Now, absolute value of x definitely is like a constant. You can pull it out, then you're left with limit as n goes large. Now, what do I mean by it's like a constant? It's a variable, right? But this is n approaches infinity, right? So that means that this guy can be taken out. That's what I mean by that statement. So, but this limit equals 1. So that means the whole of that work only gives us this guy. Okay. Now, this is, keep in mind that you use ratio tests. Okay, so let me say using ratio test. But now with the conditions of ratio tests, you only have 3 things. Either you have it, the limit less than 1, greater than 1, or equal to 1. But this is absolute value of x. So what do I do? What do I do? So now let's see. So we then say by ratio test, the series converges. Of course, is either you say converges or you say converge absolutely. They are, in this case, they are the same because absolute convergence implies convergence. Okay. Right? And diverges. Okay. Now, I want to remind you guys about something I wrote when I started the class. I wrote 3 important things. I'm just going to flip there, guys. Sorry, I'm flipping across your faces, but now, did you see the third point? The third point now says for each value of x, we can test for convergence or divergence. All right. It's all going to make sense now. Now, when x was 0, we said it converges, right? 0 is just 0. There's really nothing to do. It brings everything down to 0. Now, but in this case, our x is not 0, okay? When x converges, it converges for this guy, right? In interval form, this guy is the same thing as -1, 1. Okay? So now I need to now do that testing. So I have to test. Okay, so it's important, guys. You must test endpoints. So let me write that. In fact, let me write it in red pen. Okay. You must test endpoints. It's a must. If you don't do that, then that means your conclusion, we're not sure. It might not be absolutely true. Now, what does this statement mean? What does it mean to test endpoint? Let me put it in a box too. Okay, so keep in mind that we have the interval. It converges for -1 to 1, right? So what do? You test both. When x is 1, let's start from the left side, -1. Now, when x is -1, what happens? Remember that our function was given by, let's see, what was f of x? We'll go back there. F of x is this guy I can see right here, okay? -1 to the power of n minus 1. And then I think that was, maybe sure. Yes, x to the power of n, okay? So this is x to the power of n divided by n. Now, when x is -1, so you just plug in a -1 here. So that means f of -1, this is from 1 to infinity, n goes from 1 to infinity, -1 to the power of n minus 1. Now, remember, x is -1, right? -1 to the power of n divided by n. Interesting. Interesting. Now, this guy, I can rewrite it as n equals 1. Okay. Now, let me remind you guys. Do you remember that we talked about the negative of harmonic series? Okay. Do you guys remember that negative of harmonic series? This guy is just the negative of harmonic series. You can see that from 11.4 when we did alternating series test. Okay, when we did the alternating series test, you can actually see that. Now, how do I know that it's the negative of harmonic series? That's a good question to ask. So look at the guys on the top. You can multiply, right? -1 to the power of n minus 1. By indices, this becomes a plus n divided by n, right? So this is sigma notation. You got a -1 to the power of 2n minus 1 divided by n. Okay, now this, we're still doing basic simplification, guys. Basic. Come to the bottom. So this guy is n goes from 1 to infinity. -1 to the power of 2n times a -1 to the power of -1 divided by n. Now, what is 2n? 2n is an even number. When n is 1, 2 times 1 is 2. When n is 3, 2 times 3 is 6. So -1 to the power of 2n will give me 1, right? But -1 to the power of -1 will give me -1. So that means that this guy is exactly equal to -1 over n. So what does negative of harmonic series mean? I can pull out this negative sign and I'm left with talk to me, guys. Harmonic series. This guy is harmonic. So you have the negative of the harmonic series. Okay. So, and what's the behavior of harmonic series, guys? It diverges. Okay. Diverges. Why? Because it's harmonic. I remember every harmonic series always diverge. Now you've checked the first endpoints, and you see that, oh, at the endpoints, what happens diverges. Now we'll move on to the second endpoint when x is 1. And the work with power series is thorough. When you're working with power series, you do a thorough job, okay? You do a thorough job when you're working with power series. Okay, so we move on. When x is 1, what happens? I have a f of 1. Remember again, our f of x is the sum n from 1 to infinity, negative 1 to the power of n minus 1. You got a x to the power of n divided by n. Right? So this guy becomes just whatever you have x, just plug in 1. It becomes n goes from 1 to infinity, negative 1 to the power of n minus 1. Then you do have a 1 on top, 1 to the power of n divided by n. But keep in mind that 1 to the power of n is just 1, right? You have something like this. But can you guys remember what we call this guy? What did we call this guy? From 11.4. This guy is the alternating harmonic series. Okay, so and what does the alternate, what's the conclusion? Alternating harmonic series diverges. However, alternating harmonic series always converges. Okay, so conclusion. On the left end point of the interval, remember I had negative 1 less than x less than 1, right? We started with negative 1 comma 1, and this is the same thing. On this left end point, it diverge. But on this right end point, it converge. What does that mean? I will tell you guys shortly. So conclusion, the series converges for what? Negative 1 less than x. Now that point where it converges, it must include that point. So that means you have a less than or equal to 1. Okay, so you always include that point, that endpoint where it converges and diverges elsewhere. Suppose I'm working with negative 2 comma 2. Okay, if it converges at negative 2 and it diverges at 2, that means my interval is going to be negative 2 less than or equal to x less than 2. So at any point it converges, it will be less than or equal, it must include that point. Now, what if it converges at both ends? So suppose we had negative 3 comma 3. If it converges at both ends, that means you do negative 3 less than or equal to x less than or equal to 3. So because if I see this guy, okay, if you do a homework or a test and I see this guy, I know what it means. It means that the series converge in this right-hand corner, okay? That means that in this other side, the series is divergent. Okay, so remember when you work with power series, you got to do a thorough job. Okay. Now let's look at another example. N from 1 to infinity, x minus 3 to the power of n divided by n. So again, keep in mind that we have to use the ratio test. We need the interval, the values for which this guy converges. So what do we do? How do we treat this? Okay. We go by saying that let an be x minus 3 to the power of n divided by n. Of course, this is my an. Right? What is a sub n plus 1? Wherever you have n, plug in n plus 1. X minus 3, you got n plus 1 here, right? Divided by n plus 1. Now, just as I mentioned before, always find a way to simplify your a sub n plus 1. If I simplify this guy, this is going to be x minus 3 to the power of n divided by n plus 1 times x minus 3 to the power of 1, right? Now, we use the ratio test, right? Always remember that. Okay, so limit as n goes large. This is a sub n plus 1. This is x minus 3 to the power of n multiplied by x minus 3 divided by n plus 1. Now, remember the whole of this guy, you still have to divide it by a sub n. A sub n is a fraction, so it flips. Let's see, can anything cancel? This guy can cancel this guy. Interesting. So what else can I see from there? I can see that I have the limit as n goes large, n divided by n plus 1, and then you do have a x minus 3. But again, n divided by n plus 1 is positive. How do I know that? Okay, the series is being indexed from n equals 1. Okay, so that's positive number. Okay, so this guy is limit as n goes large. You do have n divided by n plus 1. And this guy is x minus 3, okay, in absolute value. All right, so I can write this guy as x minus 3. Limit as n goes large, n divided by n plus 1. What do I know, guys? This limit equals 1. That means all of this work means that I only have this guy left. Now, we use ratio tests. Ratio test has, different possibilities. All right, so by ratio test, the series is absolutely convergent. Remember, when a series is absolutely convergent, that means it converges. But when a series is convergent, it does not necessarily mean that it is absolutely convergent. Okay, so we mentioned that in 11.6. The series is absolutely convergent, and it will converge if this guy is less than 1. If you want to rewrite this guy, how can I write this? This is the same thing as -1 less than x minus 3 less than 1. Now, can I find a way to keep x alone in the middle? Yes. So what do I need to do? Just add 3 to both sides. You have a 3 plus 3 minus 1 less than x minus 3 plus 3 less than plus 3, 1 plus 3. 3 minus 1 is a 2. This guy cancels, less than x less than 4. Keep that in mind. When the center is different from 0, okay, remember that this guy is what we call the center, this 3. Okay, that's what we call the center. Right? Okay, so let's move on. Now, and it diverges. Remember ratio test, right? When this guy is greater than 1. Now, but our interest at all times is that we're looking for the interval of convergence. So I'm going to pick this guy here. So now we test the endpoints. What is the endpoint? Now let me draw a line, okay? Let me make it better. This is 2, this is 4. So let's do that, okay? So the first thing is that we have to check here. This is 2, right? This is 4. When x is 2, what happens? Keep in mind that your f of x is this guy. When x is 2, plug in 2 there. You have a series from 0 to infinity. And this is like a 2 minus 3 to the power of n divided by 2. And this is, divided by n. This is just n goes from 0 to infinity, negative 1 to the power of n over n. We just saw this, right? We just saw this, okay? This guy is an alternating harmonic series. And it does what? Converges. So now that's the left end point. Okay, that's the left end point. So what about the right end point when x is 4? F of 4 is going to be this guy. So now you notice that every time we plug in the endpoint, it gives us like a known series. Okay, so that's another way to help your understanding. It gives you something you know whether it really converges or diverges. Sorry, I should be indexing from 1, not 0. Okay, sorry about that. Let's see how long I've been doing that for. Okay, this should be indexing should be from 1 and not 0. If it's from 0, there's a problem. Okay, all good. 1 to infinity. This is 1 over n. Talk to me, guys. What is this series? This is harmonic series. Okay, what does harmonic series behavior? It does what? Diverges. So what's going to be my conclusion? My conclusion is that the series is convergent. Now remember that originally my interval is, where is it? 2 less than x less than 4 before I tested the interval, before I tested the endpoint. Now, when I tested the endpoint, it was convergent at the left corner. Okay, so that means it's convergent 4. When it is convergent at a point, then it has to include that point, but divergent at 4. Okay, so and divergent for x less than 2 or x greater than or equal to 4. Now, if I have to ask you a question that what is the domain of f? That is the domain of convergence. Okay, the domain of convergence is just going to be 2, 4. Or we can just call it the interval of convergence. It's the same. So if I ask you what is the interval of convergence, you have to work up to this point. You test the endpoint. I mean, testing the endpoint is something you really must do. Okay, testing the endpoint is something you really have to do. You really have to put that in consideration. Okay. All right, so now let's step up this discussion a little bit higher, by discussing a powerful theorem, okay? Now, give it space. Now we discuss a useful theorem. Now this theorem is going to build on what we've learned, okay? So the theorem. For a given power series, remember how we write this guy? Cn, series power series in x minus a. There are only three possibilities. There are only three possibilities. Number one possibility is that the series converges only when x is a. Number two is that the series could converge for all values of x. And number three is that there is a positive number, we call it R, which we call the radius of convergence, such that the series converges if this guy is less than R. Now, essentially what I'm putting together here, we've seen them in some bits here and there in the examples that we did, those examples, 3 examples that we studied, okay? But now this is, we're putting it together formally, okay? This is a formal way of writing it. So where R is the radius of convergence. All right, let me get to my red pen. Now, if you have a power series, you have 3 possibilities. The first possibility is that the series converges only when x is a. Now, when it converges only when x is a, that means my radius of convergence is 0. Now, when it converges for all x, the radius of convergence is infinity. Okay? And the third one is where your radius of convergence is actually a specific number. Okay? It's actually a specific number. Now, let me write this beautiful notes. Notes. Every power series has a radius of convergence. Every power series actually has a radius of convergence. Now, I talked about radius of convergence. There's something we call the interval of convergence definition. Okay, so let's define the so-called interval of convergence. All right, so the interval of convergence of a power series is actually the interval. Now watch this, guys. Consisting of all values of x for which the series converge. We have seen this before, guys, but now we're just putting it together formally. Okay, and now we're giving, like, it's more like we're giving honor to whom honor is due, that kind of thing. Okay, let me put a note again. Note in general, and we've seen all of this, I'm just putting it together. We use the ratio test. Sometimes we can use the root test. To determine R. What is R? Radius of convergence. However, the endpoints of the interval, the endpoints of the interval of convergence must be checked with some other tests. Now, in the previous examples, we were testing the endpoints, and while we tested the endpoint, we saw just a specific thing, harmonic series or alternating harmonic series. That is not always the case, okay? There are sometimes when you have to use comparison tests. There are sometimes where it has to be the p-test, okay? So it's not always going to be harmonic, okay? So just wanted to clarify that. Okay, so let's do this example here, and I believe that it will really help us to see this in a good light. Okay, so example. Find the radius of convergence and the interval of convergence of the series -3 to the power of n, x to the power of n divided by square root of n plus 1. Interesting problem. This is a power series actually, okay, because we're still talking about it. Solution. Where do we start from? Okay, we can start from saying it all depends on how you want to think about it. You can start by saying let f of x be equal to the power series, or you can just go ahead and start from saying that define your an. Your an is -3 to the power of n, x to the power of n divided by square root of n plus 1. What is going to be my a sub n plus 1? Just replace n by n plus 1, okay? Just replace n by n plus 1. You have a -3 n plus 1, okay? X n plus 1 divided by this guy on the bottom is going to be n plus 1 plus 1. Right? So this is a sub n plus 1 equals -3 to the power of n multiplied by -3 to the power of 1. Now, this is me just simplifying, right? Because I need to use the ratio test, and simplifying ahead of time makes life easy for me. So now I can now fit it into the ratio test frame. A sub n plus 1 is the whole of this guy. So sometimes you have it as long as this. It might look messy, but you gotta be careful and be able to capture everything you need. Okay, divided by square root of n plus 2. Now, again, your a sub n is a fraction. So once you put it in, there's going to be a change flip, okay? There's always going to be a change flip when it is a fraction. X to the power of n. Can anything cancel? Sure. This guy cancels this guy. This guy takes up this guy. What else can be canceled? Nothing at the moment, okay? So let's put things together. N goes large. This is an x. And then this guy, you have a square root of n plus 1 on the top. You have a square root of n plus 2 on the bottom. Of course, this guy, square root of n plus 1 divided by square root of n plus 2 is positive. You can take it out of the absolute value sign. So you would have a square root of n plus 1 divided by n plus 2 times this guy. Oh, I'm missing something, guys. Now we have a 3 there, right? So that is absolute value of, okay, let's put it here. Okay. So absolute value of -3 is just +3. This guy is the same thing as 3 absolute value of x, limit as n goes large, square root of n plus 1 divided by n plus 2. Okay, so we've done a lot of things about limits in the past. What is the limit of this guy? The limit is just 1. This is like 3 absolute value of x. When we get to this point, can we remember what we really do? Now, this is ratio test. I need this guy to converge. So this guy has to be less than 1 initially, okay? So I'm going to say by ratio test, the series is convergent when this guy is less than 1. Interesting. This means that my x is less than 1/3. I divide both sides of this inequality by 3. 3 is a positive number. Okay. So now can I rewrite this guy in terms of, I want to get rid of this absolute value sign. What can I do? This is the same thing as -1/3 less than x less than 1/3. Now let me help you guys with a trick. When you get to this point, it's easy to find your radius of convergence from something like this. Now in this case, I can write this guy like x minus 0 less than 1/3. Okay, so you have your center and you have your radius of convergence. Now, but be careful. If this number is not 1, if this number is not 0, then this automatically does not become your R. You have to simplify, okay? Now, when we get to this point, remember, what do? We test endpoints. Now, the first left endpoint, when x is -1/3. That means, remember, my series is actually something like this. Let me pick it up. When x is -1/3, what happens? Just plug it in. You have this guy. Divided by square root of n plus 1. Now, sometimes you now have to rely on your understanding to put things together, how you can do some algebra. Really going to do an algebra here. This guy on the top, they have the same power, okay? So I can fuse them together and they can actually multiply themselves. You're really going to have a 1 divided by square root of n plus 1. Let me see, I want to be careful, guys. Oh, it's from n is going from 0. So please be careful of the indexing, okay? The indexing changes a lot of things. So please don't be sloppy about it the same way I have been sloppy about it here. Okay, so this is from 0, I mean. Now, if I decide to list this guy if I decide to plug the numbers, So that means I have plug in 0, you have 1 over 1. Plug in 1, you have plus 1/2 plus square root, I mean. What can we see? I can rewrite this guy. It means exactly I can write this guy as a series start from 1. Think about this, guys. Think about this. So beautiful. Let's see. Let's list the elements and see if they are the same. When n is 1, you have a 1. When n is 2, you have a 1 over square root of 2. When n is 3, you have a 1 over square root of 3. Exactly the same. Okay? So, but this guy is the same thing as n to the power of 1/2. Think about this, guys. What can you do here? Do you remember the P series? This is just a P series with P equals 1/2. Okay? And P is less than 1. What does that mean? With the P series, it does what? Diverges. That's the left endpoint. What about the right endpoint? When x is 1/3. When x is 1/3, plug it in. N goes from 0 to infinity, -3 to the power of n times -1/3. No, sorry, it's positive here. Because remember, your series is actually like this guy, x to the power of n divided by square root of n plus 1. So you plug in x. Okay, so let's simplify this guy. This guy's on top can multiply. If it does, you're left with a -1 to the power of n. Now, you need a series test to determine whether this guy converge or diverge. Now, which one comes in handy? What series test comes in handy? The alternating series test, okay? So I can just say, let Bn equals this guy. Okay, the limit as n goes large of this Bn zero. Okay, remember, alternating series test has two conditions. The Bn must be decreasing and the limit of Bn has to be 0. Now, let me show you, in the past, we have always shown this decreasing part by first derivative test. Okay, we can always do that as well. Okay, okay, we can always do that. All right, so let's see how we go about that. We can always do that. Now, what do we do? Now, I want to show you guys a different thing you can do. And this different thing you can do is by using the idea of when a sequence is said to be monotone decreasing. Okay, so okay, so that I don't, mess up with what you guys know already. So I'm just going to stick to the derivative test that you know, okay? And I can write that one on the other side. So if I stick to what you already know, this guy is something like this, right? What is f prime of x? F prime of x is going to be a negative here, 1/2. Okay, then you have a multiply by 1 over square root of x plus 1 multiplied by x plus 1. So, but the bottom line is that this guy is less than 0. Okay. then Bn is decreasing. But what is the other one I said I wanted to write? The idea of the monotone decreasing. You check for, let me just put it in box. Another method. Okay, no. This is just another method anyway, but I don't have to write that as a topic. So you do Bn is just 1 over square root of n plus 1. Then you go to B sub n plus 1. The next term is n plus 2. So you compare these two guys. B sub n plus 1 is actually less than this guy. And that means that Bn is decreasing. It's just like I'm counting, right? If you're counting numbers and the next number is less than the previous number, then you can be sure that it decreases, okay? Another approach. So let me just, another approach to show Bn is decreasing. Okay, so the two conditions for alternating series test are satisfied. So what does it mean? So this series we're talking about here is convergent by the alternating series test. Now, can we go to our conclusion? Now, let's go back to the question, guys. The question is about what? It's asking us to find the radius of convergence and interval of convergence, okay? The radius of convergence, I've determined it already, but I've not just mentioned it, maybe. Okay, so to know the radius of convergence, after you have this this interval you have right here, let me just circle this part. After you have this guy, you have to write it in this form, okay? If you write it in this form, make sure that the only thing you have on the middle is x. Make sure anything you have on the middle is just x. Then this guy, any of this guy is the interval of convergence, but the radius, my bad, the radius of convergence, but it's positive, okay? You don't say r is negative 1/3. It's just a positive guy. Okay, so that's the way to drive my conclusion home. Conclusion, the radius of convergence is r equals 1/3. What about the interval of convergence? How do you know the interval? Keep in mind that that is when, if you look at the previous example we did, okay, we're looking for the interval of convergence, which we did call the domain at that point, right? Where you test the endpoints. If the left endpoint is convergent, that means it includes that point. If the right endpoint is convergent, it means it includes that point. But in our case, the left endpoint was divergent, but the right endpoint is convergent. So that means the interval of convergence, left endpoint diverges, open parenthesis, negative 1/3. Right endpoint convergence, this guy. If you don't want to write it this way, perfect. Okay. So again, the power series is a special type of series, and it needs some kind of details, which you always need to think about. You need some details, gotta fill in the details, and that really helps you to make a logical conclusion. Okay, so I'm going to write two different series. You guys can just try. I will tell you what the answer is. find the radius and interval of convergence for, first one I'd like you guys to try. I'm going to tell you guys what the answers are. The radius of convergence R is 3. We call the interval of convergence, we use I. Okay, so I is -5, 1. So the second thing, maybe I should just use real numbers here. So let me use A and B, okay? Second guy I'd like you guys to try. X to the power of 2n plus 1 divided by 2n plus 1 factorial. My radius of convergence is 0. No. In this case, let me see. No, it's infinity. And then my interval of convergence is -infinity, infinity. Okay. So I'd like you guys to work on this one. Try your hands on them. I already gave their answers. See if you get them. Okay. I hope this all makes sense. I'll see you in the next session. Bye-bye.